Hello everybody. So this is going to be a review of Newton's second law practice worksheet. Okay, so the first part of this worksheet is just a review of like kind of what we talked about in Newton's first law and connecting it to Newton's second law. So let's get started. So the weight of a humpback whale is 66,000 pounds. What is the whale's mass? So what are we given in the problem? Well, the one thing that we're given is 66,000 pounds. So let's go ahead and write that down. So 66,000 pounds. So one conversion that I know that I can use in order to get its mass is 1 kilogram is equal to 2.2 pounds. So if I don't know the mass, but I'm given 66,000 pounds, one thing that I can do is pretty much cross multiply here, right? So I can take these two numbers, multiply them together, and divide out by that. So let's just see what that looks like. So I'll take 66,000 pounds, multiply it by 1 kilogram, and divide it by 2.2 pounds. So as you can see here, these pounds are going to cancel, and I'm going to be left with kilograms. Woo! It's exactly what I want, right? So I have 66,000 kilograms divided by 2.2, and I will get 30,000 kilograms here as my answer. So the mass of a 66,000 pound whale is 30,000 kilograms. All right, so we got that one. Let's jump to the next problem. So what is the whale's weight in newtons? So we're looking at the same whale, and now we're asked for the weight in newtons. Well, one thing that we know to be true is the mass, right? The mass is not going to change. The mass is constant. So the 30,000 kilogram mass is what we're going to use in order to find the whale's weight in newtons. So we have the mass of the whale is 30,000 kilograms. And now we need to solve for its weight, right? So let's just say that Fw is equal to the weight, because weight is a force. So we say that Fw is equal to mg. Right, because this whale is on Earth, and what is causing all of us to have weight? G, right? So Fw is equal to your mass of 30,000 kilograms times 10 meters per second squared. Okay, so this will give us a weight of 300,000 newtons. Okay, again, that's because weight is a force, so we need to give it a unit of force. Okay, so again, we took the mass of 30,000 kilograms and we multiplied it by g, which is that gravitational attraction that we all have to the Earth, and it's 10 meters per second squared in this class. Okay, moving on to the next one. So Gunther, the weightlifter, can lift a 230 kilogram barbell overhead on Earth. The acceleration due to gravity on the sun is 274 meters per second squared. What would be the weight of the barbell on the sun? And I believe in your worksheet it's asked a little bit differently, but I know that I said prove it, right? So when I ask you to prove it, I want to see your data behind it, right? Prove it to me. How do you know? Okay, so let's look at this problem. Again, we're given a mass, and then we're given an acceleration due to gravity. So let's go ahead and write those two things down. So the mass of that barbell is 230 kilograms. Okay, and we're also given that G on the sun, or that gravitational attraction on the sun, is 274 meters per second squared. And again, how do we get that gravitational attraction? Well, it all has to do with our attraction to the massive object, right? So like the Earth, right? We're gravitationally attracted to the Earth, right? 10 meters per second squared. Well, on the sun, that star has a lot of mass, so we are very attracted to it. How much are we attracted to it? 274 meters per second squared. Okay, so the way that we're going to find the weight of the barbell on the sun is very similar to the way that we are going to find weight here on Earth, right? Except we're exchanging that G. So now we're using G on the sun. So F weight, again, it's a force times 230 kilograms. Because your mass is constant, it's not going to change no matter where you are, and you're going to multiply it by your gravitational attraction on the sun. Okay, so FW equals, again, go ahead and pull out your handy dandy calculator. So 230 times 274, we get 63,020. What are my units here? Well, it's a force, so we measure it in newtons. All right, so let's look at the next one. So now I ask, well, what's the barbell's weight on Earth? Like, if you're telling me that the weight is so much bigger on the sun, well, prove it to me, right? So let's prove it. So let's say that the mass is the same because it is the same. It's a constant no matter where you are, so that barbell is still 230 kilograms. And now G on Earth. That gravitational attraction that we have to Earth is 10 meters per second squared. And now again, we solve for weight the exact same way. So FW is equal to 230 kilograms times G. So it would be, oops, I already started writing the sums. It would be 10 meters per second squared. Right, so FW would be 2,300 newtons. So as you can see, we proved it out, right? So the weight on the sun is a whole lot more than the weight on Earth. As we expected, right? This has to do with the star's mass, right? So if we were able to stand on the sun, we know that the sun has mass, and its mass is going to cause us to be attracted to it. So let's look at the Newton's second law stuff. Again, that kind of dealt with Newton's second law, but we learned it during Newton's first law. So now this is kind of new stuff where we're dealing with an acceleration that is not really understood to us yet, right? Because it's always different. Where G is always constant and we were always worried about the weight on Earth, now it's going to change depending on our force and our mass. So let's read about it. So Red Sox designated hitter David Ortiz swings at a 0.15 kilogram baseball and accelerates at a rate of 3.0 times 10 to the 4th meters per second squared. How much force does Ortiz exert on the ball? So again, there's a whole lot of information here, right? So let's just break it down and look at the units that we're given. So we're given a kilogram and we're given meters per second squared. Awesome, right? Now it helps us identify what we're actually given. So we're given a mass, right? Because we measure mass in kilograms, and then we're given an acceleration because we measure acceleration in meters per second squared. So let's write both of these things down. So we have a mass of the baseball, which is 0.15 kilograms. And then we're also given an acceleration of 3 times 10 to the 4th meters per second squared. And bringing it back to Newton's first law, what do we know about mass and inertia? Well, if you have a large mass, then you have a lot of inertia. And by inertia, we mean resistance to change your state of motion. So this ball, right, it's not even a kilogram. So it doesn't really have that much mass considering what we really deal with. So it doesn't have a lot of mass, so we know that it doesn't have a lot of resistance to change its state of motion, which is why it accelerates so rapidly. Okay, so let's find out how much force David Ortiz needs to exert on the baseball in order for it to accelerate 3 times 10 to the 4th meters per second squared. Okay, so using Newton's second law, F equals ma. Okay, where F is our force or our net force, m is 0.15 kilograms, it's our mass in kilograms, and a. Now this might ring a bell to you, right, when we were talking about scientific notation, but all this is saying to you is that 3 times 4 zeros, so 1, 2, 3, 4. Okay, so if we were to write this down again and plug it in our calculator, 1, 2, 3, 4, we would get 4,500 newtons. So David Ortiz is swinging around that bat, and that force of that bat is 4,500 newtons. In order to accelerate this mass of 0.15 kilograms, 3 times 10 to the 4th meters per second, or 30,000 meters per second squared. Whoa! Right? All right, let's move on to this next one. So Claudia stubs her toe, which we've kind of all done before, right? It really hurts. Claudia stubs her toe on the coffee table with a force of 100 newtons. What is the acceleration of Claudia's 1.8 kilogram foot? So on this one, we're given different information, right? So we're given the force of which Claudia is stubbing her toe. And we are also given the mass of her foot, which is 1.8 kilograms. And we're actually asked to solve for acceleration. So another way to write Newton's second law is to say that acceleration is equal to the sum of the forces all over m. Well, what is the sum of the forces in this situation? Well, it's just the force that we're given, 100 newtons. And what do we need to divide it by? The mass of the foot. Okay, so again, if you break out that calculator, 100 divided by 1.8, we get an acceleration of 55.56 meters per second squared. Okay, because again, when we measure this out and work with Newton's second law, right, forces don't change your velocity, they change your acceleration. Okay, so when we have this force and we're dividing it by how much mass we are given, we have to find the acceleration here. So let's jump to the next one before we run out of time. So Brian Shaw exerts a force of a massive stone ball that has a mass of 450 kilograms and it accelerates at a rate of 30 meters per second squared. How much force does Brian Shaw exert on the stone ball? So we have a mass and we have an acceleration. So the mass of the stone ball was 450 kilograms, and the acceleration of which Brian Shaw was exerting on this was 30 meters per second squared. And we are asked to solve for the force. So using Newton's second law, F equals ma, we can do so. So plugging in our mass in kilograms and multiplying it by the acceleration that we are given. So plugging this in, we get that Brian Shaw is exerting a force of 13,500 newtons. Okay? So if the stone ball was more mass, would Brian need to exert more force? Absolutely, right? So working back to Newton's first law with inertia, if you have more mass, then you have more resistance to change your state of motion. So you're going to need a larger force in order to accelerate. So absolutely, you will need more force. So during the annual pumpkin chunking contest, a 3.6 kilogram pumpkin is shot out of a cannon with a force of 500 newtons. What is the acceleration of the pumpkin once it leaves the cannon? So we are looking for context clues here. So we are given 3.6 kilograms and we're also given a force of 500 newtons. So let's write those down. So our mass is 3.6 kilograms. Our force is 500 newtons. We are trying to solve for the acceleration once it leaves that cannon. So we take A is equal to the sum of the forces all over your mass. Again, the sum of the forces in this case is just the force exerted on that pumpkin. So breaking out the calculator again, we take 500 divided by 3.6 and we get 138.89 meters per second squared. Okay, I hope this was helpful to you. If you still have questions or want to see more examples, please let me know. See you all soon.